part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss Amperes Law and also the divergence-free nature of the magnetic field. Yesterday, we discussed the Biot-Savart Law, and that's where I'm going to begin in this discussion. Magnetic field is equal to the permeability of free space over 4 pi times the volume integral of the curl of the volume current density J and the separation vector all over the magnitude of the separation vector cubed. In the first part of this lecture, I'm going to show that the divergence of the magnetic field vanishes. So as it turns out, this expression holds not only for static fields, but also for time-varying fields as well. I'm also going to show that the curl of the magnetic field is proportional to the volume current density, and the constant of proportionality in this case is the permeability. I'm going to begin with the divergence first. Since this divergence operates on unprimed coordinates, I can pull that inside the integral, which is over prime coordinates. Time to consult a table of vector identities because we are basically calculating the divergence of the curl of two vectors. And so that is equal to the dot product of the vector g and the curl of vector f minus the dot product of vector f and the curl of vector g. Okay, so I've expanded this out into two terms, and we have the separation vector of the magnitude of the separation vector cubed dotted into the curl of the volume current density minus the volume current density dotted into the curl of the separation vector of the magnitude of the separation vector cubed. This first term vanishes because the curl operates only on unprimed coordinates, and the volume current density is a function of prime coordinates, so that's equal to 0. In the second example, it is always the case that the curl of the separation vector over the magnitude of the separation vector cubed is equal to 0. So therefore, we have shown that the divergence is equal to 0. I'll just leave it up there for a bit more, and I'll erase it and we'll move on, okay? So we've proved our first expression on the basis of the Biot-Savart Law. Now this curl, likewise, operates only on unprimed coordinates, so once again, I can pull it inside of the integral. have the curl of the cross product of two vectors. So once again, you want to consult a table of vector identities. Curl of cross product of two vectors is equal to second vector dotted into the gradient of the first vector minus the dot product of the first vector and gradient operating on the second vector. And we have our vector f times the divergence of g minus g times the divergence of f. I'm going to expand out the integrand. First term is going to give me expanded the integrand out into four terms. In the first term, we have separation vector over magnitude separation vector cube dotted into del operating on falling current density. Now, this operator operates on unprimed coordinates, but j is only a function of prime coordinates, so therefore, this term goes to 0. Second term, I need to work on that a little bit more, so I'll leave that for the time being. The third term, you'll notice, is the product of the volume current density and the divergence of the separation vector of the magnitude of separation vector cubed. Well, that divergence is just equal to 4 pi times the delta function of r minus r prime. And then last but not least, we have separation vector over the magnitude of the separation vector cubed times the divergence with respect to unprimed coordinates of the volume current density, which is a function of prime coordinates. So this last term vanishes as well. I want to look at the second term now. Now I can change out this operator for one that operates on prime coordinates, because this is just operating on r minus r prime over r minus r prime cubed. And it turns out if I change this to primed, this will give me positive j as a function of the prime coordinates dotted into del with respect to prime coordinates of r minus r prime over r minus r prime cubed. I'm going to first consider just one component. In other words, let's just look at the z component. There's nothing special about the z component. What holds for that will hold for the x and y components as well. again, we need to make use of a vector identity, and this time we'll use an identity that we've seen several times throughout the semester. That is to say that if you have the divergence of the product of a scalar and a vector, that's the same thing as taking the product of the scalar and the divergence of the vector plus the vector dotted into the gradient of the scalar. So this term actually is this one. So I'm going to rewrite this as so now I have the divergence of the product of the scalar and the vector volume current density minus the scalar times the divergence of the volume current density. Now this final term vanishes because even though this divergence is operating in prime coordinates now, we're dealing with steady currents. The second term is equal to 0. We are calculating the volume integral over this, so we reduced this to this term involving delta function and this term, but imagine we've got z, x, and y components. I'm just going to calculate the volume integral of this first off. I can convert this volume integral, which is volume integral of the divergence of a vector, to a surface integral. Now the surface integral vanishes because, as a matter of fact, I can take that surface integral as large as I like. Volume current density is going to be 0 out there. So therefore, this term vanishes. So out of all these three terms, the only one that survives is the one with the delta function. So therefore, curl of the magnetic field is equal to mu naught over 4 pi volume integral of the volume current density times 4 pi times the delta function, and that is equal to mu naught j. Now we've shown two equations hold. The first is that the magnetic field is divergence free. The second is that the magnetic field is proportional to the volume current density. I'll leave this up for a bit more, and we'll move on. it's convenient to convert this equation, Amperes Law, into integral form. Of the curl of the magnetic field, integrated over some surface, and that's equal to the integral over that same surface of the dot product of the volume current density and the normal to that surface. By use of Stokes' law, or Stokes' theorem, I can convert this surface integral into a line integral. And this is Amperes Law in integral form. What it enables me to do is to, if I take the line integral of the magnetic field around some closed path, that is equal to something that is proportional to the amount of current that flows through that loop. I'll be working out several examples in the rest of this lecture on making use of Amperes Law. And what we'll see is that there's a similarity in use between this and Gauss's law. Gauss's law we applied to systems that exhibited a high degree of symmetry. By exploiting that symmetry, you can solve for the electric field quite readily without having to resort to a bunch of nasty integrals. In the same way, I can use Amperes Law to determine the magnetic field of systems that exhibit a high degree of symmetry without resorting to a bunch of complicated integrals. Okay, before I move on to that though, I do want to say a few words about the divergence-free nature of magnetic fields. And to draw some parallels and also differences with electrostatics, the divergence of an electric field is equal to volume current density divided by the permittivity of free space. We also have in electrostatics that the curl of the electric field is equal to 0. Now, the divergence of the magnetic field holds not only in static situations, but also in time-varying fields as well. Over here, we talked about field lines and how to draw them. Basically, the rule is that you start on positive charges and you terminate on negative charges, and those field lines can't cross ever. Over here, the rule that students are instructed is that magnetic field lines form closed loops or they go off to infinity. The reason why they don't terminate on anything in space, the reason they're given, is because there's no magnetic monopole, and there's no magnetic counterpart to electric charge. Okay? However, in general, magnetic field lines do not close. After a single circuit of balanced wire. In any textbook problems that you encounter, that's true. They do close after a single circuit. We talked about straight wires, we've talked about ring carrying currents, and we've talked about Helmholtz coils. In all of those cases, magnetic field lines start at one point in space and they wind up back where they started. Or they went off to infinity. We gave you rules of thumb for calculating the electric field, but it might be nice to know actually how they are, field lines really are calculated. So in fact, a set of equations we want to solve is dx over the x component of b is equal to y, the dy over the y component of b is equal to dz over the bz component, or about the z component of b. In any case, you have to solve these numerically. Sometimes people use the orange cutting method to do that. Anyway, this is for traditionally called lines of force. that term, for obvious reasons, has fallen into disfavor because they aren't lines of force, they really are just field lines. If you haven't already done so, I encourage you to look at the set of simulations of magnetic field lines that are on the BocaPhysics site. If you go to the website BocaPhysics.com, I've got a list of simulations and you'll see magnetic field lines. The first set of simulations are on systems that you encounter in general physics class or in electromagnetism class. In other words, straight wires that are parallel, that carry current in the same direction or that carry current in opposite directions. And I also have a few with a current carrying ring and Helmholtz coils and also toroid as well. In all those cases, magnetic field lines exhibit that classic textbook behavior. The last three simulations I show you, magnetic field lines, don't close after a single circuit. So the last two of the simulations involve having perpendicular current carrying wires and a magnetic field superimposed upon them. And what you'll see is you've got really complicated structure there for a surprisingly what appears to be a simple system. And the last simulation I show you is we have a current carrying ring and there's a long straight current carrying wire at the center of that, and there's also a uniform magnetic field superimposed upon that. And what you'll see is the magnetic field line doesn't close after a single loop. It in fact travels about the ring. And in fact, fusion researchers are in the business of determining magnetic fields due to certain current configurations. They're looking for the optimum current configuration to have to enable confinement of the plasmas. So fusion researchers classify magnetic field lines that are important in their field of study as being rational, ergodic, and stochastic. Rational meaning that the field lines close after a finite number of circuits. Ergodic meaning that the field lines close only after an infinite number of circuits. Another way of saying is that the lines lie on the magnetic surface. And stochastic meaning that the field lines occupy a volume of space. To the fusion researcher, they're interested in ergodic field lines because those have favorable confinement properties. And there are also chaotic magnetic field lines as well. Anyway, the point being is, generally speaking, magnetic field lines don't close after a single circuit. Life is a lot more complicated than what you see in an electromagnetism textbook. I have a list of references on the BocaPhysics website, so if you're interested in this topic, I encourage you to go take a look at those. But anyway, for any of the problems that we do in this class, they do close after a single circuit. Life is nice and simple. The real world, however, life is far more difficult, even if you have certain configurations that appear to be simple. Okay? And I'll just close out with saying that it's often said that this behavior of closing after a single loop is a consequence of the divergence from nature. In fact, there's nothing in the theory that demands that field lines close after a single loop. Okay? And we'll move on to some examples now, making use of Amperes Law in integral form. We're going to work through 4 different types of problems using Amperes Law. We'll look at long straight wires, we'll look at current sheets, a solenoid, and a toroid. And let me erase part of this to give myself a little more room. Let's first take the example of a long straight current carrying wire. Now let's suppose that current is directed out of the board. First order of business in applying Amperes Law is to determine the direction of the magnetic field. Well, I can just apply the right-hand rule. Thumb's in the direction of the current, the fingers curl around in the direction of the magnetic field. So therefore, my fingers will curl around in a circumferential direction. So magnetic field lines curl about wires or wrap around wires, if you want to think of it that way. Okay, so let's apply this by symmetry. We know that the magnetic field is going to have the same magnitude at all points equidistant from the wire. So I'll choose a circle such that the circle's center lies along the axis of the wire. Therefore, left-hand side of Amperes Law gives me 2 pi s times b. Magnitude of the magnetic field is constant there, so basically I'm just integrating it around the length of the loop, which is just a circle, circumference 2 pi s. On the right-hand side, we have mu naught times the total enclosed current, which in this case is just I. So therefore, B is equal to mu naught I, 2 pi s in a circumferential direction. There's another way of determining the direction of the magnetic field rather than just automatically applying the right-hand rule. Let's look at Biot-Savart Law. Magnetic field is equal to mu naught over 4 pi times the volume integral of the volume current density and the cross product of that and the separation vector over the magnitude of the separation vector cubed. And similar expressions if you have a surface current density or just a plain line with, where you assume that it doesn't have any dimensions. Okay. So in this case, the current's flowing out of the board. We've got 3 possibilities. Either the magnetic field has a component in z direction, in the s direction, radial direction, or the phi direction, or some combination thereof. The magnetic field is perpendicular to the current by the form of this expression. Since the current's flowing out of the board, the magnetic field can't possibly have a component in that direction, so we eliminate that possibility. Now, let's suppose for the sake of argument the magnetic field has a component in the radial direction. So in other words, the magnetic field is pointing away from the wire. Okay? So, also from the Biot-Savart Law, if we flip the direction of the current, so in other words, instead of having J, we have minus J, that means the magnetic field is also going to be minus B. So, if I suddenly flip directions current, so in other words, magnetic field, for the sake of argument, is pointing away from the wire, and I flip the direction of the current, then all of a sudden the magnetic field would have to point towards the wire. Well, think about this. That's the same thing as just turning the wire, just flipping it around so that the current's flowing into the board. The magnetic field cannot possibly change from pointing away from the wire to pointing towards the wire or vice versa just because I turn the current around, or because I turn the wire around. So I eliminate that possibility. We are left with the only possible solution there is that the magnetic field has a component in the circumferential direction and only in the circumferential direction. Let's take a look at another kind of wire. Let's suppose we have a wire that has dimension, it has radius r. But this time it's a surface current density. I want to determine the magnetic field everywhere, both inside the wire and out. Well, first order of business is determine the direction of the magnetic field. By the same arguments as before, just apply the right-hand rule, that's the most expedient way. Your thumb's going to be pointing out of the board, so therefore your fingers will curl around in the direction of the magnetic field. And so we conclude that the magnetic field will be in a circumferential direction, just as before. Or we could go through the lengthier process of elimination argument. Okay, so because of the symmetry of the problem, we know that the magnetic field is going to have the same value equidistant from the center. It's a circular, has a circular cross section. So the Amperian loop I choose is also going to be a circle, the center of which lies on the axis of the wire. We have an Amperian loop inside and outside. Amperes law tells me that the line integral of the magnetic field around a closed loop is equal to or proportional to the total amount of current enclosed by that loop. Well, since the current is flowing on the surface of this wire, there's no current in the interior region, and therefore the magnetic field vanishes there. Outside, evaluate the left-hand side of the integral immediately because I know magnetic field is constant at all points equidistant away from the axis of the wire. So that's V times 2 pi s. On the right-hand side, mu naught times the total amount of enclosed current. Well, the total amount of enclosed current is just I. Or another way to do it is say, well, I know what the surface current density is, but you integrate that over the surface, or this, basically this the circumference here. So that's just going to be I over 2 pi r times 2 pi r, which is I. And outside, we find, once again, magnetic field has value mu naught I over 2 pi s in a circumferential direction. Last example of this kind, let's suppose you have a wire, once again, has dimension, has radius r, but this time it has a uniform volume current density. So the current is distributed throughout the volume of the wire. It's not restricted just to the axis. Since the volume current density is assumed to be uniform, that's just the total current I flowing through the wire over pi r squared, the area of this cross section. Okay, so once again, we want to figure out what's the magnetic field both inside and out. This time the magnetic field inside won't vanish because there'll be current flowing through any Amperian loop I happen to choose. Same argument as before, magnetic field is directed in a circumferential direction. Again, just using the right hand rule, thumbs in the direction of the current, fingers curl around in the direction of the magnetic field. Because this is uniform, I know that the magnetic field is going to have the same value around any loop, circle that lies along the axis of the wire. So my Amperian loop inside and outside. Inside, we have 2 pi s b. On the right, take the dot product, the surface integral of the dot product of the volume current density and the normal. The normal to this Amperian loop is just in the z direction, and that's the way the current's flowing. So therefore we have mu naught times j naught times pi s squared, where pi s squared is the radius, or rather the area contained within this Amperian loop. And therefore, inside B is equal to mu naught j naught s over 2, and once again in the circumferential direction. Outside, we have 2 pi s times b, mu naught. Now this time, no matter how large I make my loop, outside of the wire, I can make it way out here, the right-hand side is still going to be the same because this wire carries current I, and it's only contained within this area, so therefore we have j naught times pi r squared, okay? But that's total current I, and therefore outside, we once again have a magnetic field that has value mu naught I over 2 pi s in a circumferential direction. So in each of these cases, the magnetic field has the same value. It's just mu naught over 2 pi s times the total current carried by the wire in the circumferential direction. First case, we assume that it's just a wire that doesn't have any thickness to it. Second case, we assume that the wire has radius r, but because the current's flowing on the surface, the magnetic field inside vanishes. Over here, the current is distributed throughout the wire, and we wind up with a non-zero value for the magnetic field. And mu naught J naught S over 2 in the phi direction. It only vanishes along the axis of the wire, and the magnetic field is equal to mu naught I over 2 pi s in the phi direction outside. Okay? Let's turn our attention now to current sheets. Current sheet carries surface current density K. And we'll assume that the current is flowing out of the board. First order of business is to determine what's the direction of the magnetic field. Well, I could use the right-hand rule. Thumbs pointing out of the board, fingers curl in a direction. Now, we assume that this current sheet is infinitely big, so therefore, my fingers are going to be pointing to the left above the sheet and to the right below it. So therefore, magnetic field left above sheet and right below it. There's another way to determine the direction of the magnetic field by using the Biot-Savart Law. There are three possibilities here. Either the magnetic field is directed out of board or into it, up or down, or right or left. Because the magnetic field is perpendicular to the current, I can immediately exclude the possibility that the magnetic field has a component pointing out of the board or into it. What about up or down? Well, again, because if I change the direction of the current, the magnetic field is also going to change direction. So let's suppose, for the sake of argument, the magnetic field has a component pointing upwards. Okay? So if I turn the current sheet around such that the current's flowing into the board, or I just reverse the direction of the current, then that would mean that the magnetic field would suddenly switch to pointing downwards or pointing in a different way, as I turn around. Now that's not physical. That's not possible, so therefore I exclude that possibility. We're only left with the magnetic field can either point to the right above it or left above it, or right or left below it. Okay, but right-hand rule, magnetic field points to the left above the sheet and to the right below it. Okay, so let's actually solve this. I'm going to draw a current sheet, and I'm going to look it dead on. And in this case, the Amperian loop I choose is not going to be a circle, it's going to be a rectangle. So we'll have this current, or rather loop, going in a counterclockwise direction. Left and right-hand sides will contribute nothing to the integral on the left. The reason why is because these sides are perpendicular to the direction of the magnetic field. Take the dot product of something, or two vectors that are perpendicular to each other, that's going to give 0. So this is 0 here, this is 0 here. On the left-hand side, the magnetic field is pointing to the left above it. We'll assume that this loop has length L, so therefore we wind up with BL. Below the current sheet, we also have a contribution. We've got the magnetic field pointing to the right and times the length of the loop. So we have BL plus BL, and the total amount of current contained within that, so the current contained within this loop, is just the surface current density K times L. I've got a mu naught out front there. Therefore, B is equal to mu naught K over 2. And it's negative above the current sheet. And it's positive below it. Let's take another kind of current sheet, but this time let's assume that it's a current slab. And once again, the current's flowing out of the board. We have uniform volume current density, so it's J naught Z. We want to determine the direction of the magnetic field. I'm going to draw another little rectangle here. We're looking at this current slab dead on. Let's suppose that this is y equals 0. So the midplane of the current slab lies at y equals 0, and it has thickness 2a. Which way is the magnetic field pointing? Well, by the same arguments as in the previous example, the magnetic field is pointing to the left above and to right below. At the midplane, the magnetic field has to be 0 by symmetry arguments. Okay? I could go through this whole rigmarole. Number one, I have the right-hand rule. Thumb points in the direction of the current. Fingers go in the direction of the magnetic field. Or I could do process of elimination and exclude the possibility that the magnetic field would have a component out of the board or into the board, because magnetic fields are perpendicular to the current. And I can exclude the possibility that it's pointing up or down, because simply by turning the current slab around, I could cause the magnetic field to flip from pointing upwards to downwards or vice versa, which is, that is clearly non-physical, so I exclude that possibility. Then we're left with right or left. Okay, so let me construct an Amperian loop. We'll choose a rectangle once again, and we'll choose the bottom of the rectangle to lie along the y equals 0 midplane. Okay? Now, left and right hand sides of this interval contribute nothing, because magnetic field is pointing to the left, but yet this segment of the path is pointing downwards. This segment is pointing upwards, so dot product of two perpendicular vectors gives 0, so this is 0 over here, 0 over here. The bottom part of this loop contributes nothing. Why? Because it lies along the midplane, and as we have just reasoned, the magnetic field is 0 there. So just got a contribution from this upper part. Magnetic field is pointing to the left. That's the way the path is going from right to left, so we have BL. On the right-hand side, we've got mu naught times the total amount of current that is enclosed by the loop. So let's suppose this goes from 0 to some distance y above the midplane, and it's of length L. So on the right-hand side, we have J naught times the area of this loop, which is equal to Ly. Therefore, magnetic field has value mu naught J naught Y in the x direction, and it's pointing to the left, as we reasoned just a few minutes ago. by a similar set of arguments, I can also show that the magnetic field has the same magnitude below the y-axis, okay? But this time it's going to be pointing to the right. Well, y is negative below the y equals 0 midplane, so actually that's going to be a minus as well. So in both cases where we talk from anywhere between in the slab, the magnetic field has value minus mu naught j naught y in the x direction, which means that above the midplane it's going to be pointing to the left, and below the midplane, magnetic field is going to be pointing to the right. Now what about outside? So above the slab, what value must it have there? Well, this time I'm going to construct an Amperian loop such that the upper leg is outside of the slab. Again, the left and the right-hand sides will contribute nothing because those are perpendicular to the magnetic field. The bottom leg, once again, it contributes nothing. I'm only left with this portion of the loop. So that's B times L and times mu naught times the total amount of current enclosed. Well, the total amount of current enclosed is going to be J naught times the area of the current, the slab that's within this loop. So any portion above this contributes nothing because the current vanishes there. So we have mu naught J naught L, which tells me that above the plane, the slab, the magnetic field has value minus mu naught J naught A in the x direction. And it has value mu naught J naught A in the x direction below. So in this first case, it's minus sign indicating the magnetic field is pointing to the left above it, and there is no minus sign down here because it's pointing to the right below it, okay? So notice in both of these examples, it doesn't matter how far away you get from the current sheet or current slab, the magnetic field has the same value. So in other words, constant everywhere above and below this sheet, and again, constant everywhere and below outside of the slab. That should sound familiar to you. When you think back to current charge sheets, which we discussed in electrostatics, the electric field had constant magnitude everywhere above and below it. If you had a positively charged sheet, the electric field pointed away from it, and it has value surface charge density sigma over 2 pi over 2 epsilon naught. Okay? So again, just as with the electric field, due to a charge sheet was constant everywhere, the magnetic field due to a current sheet is constant everywhere outside of the current sheet or current slab. Okay? Directions are different, of course. Electric fields either pointing away from or towards the sheet. In this case, you have the magnetic field either pointing to the right or left below it. Okay? So let's turn our attention now to solenoids. And here's where we're going to have to make some more approximations, okay? Typically, this is not such great artwork here, but anyway, we'll assume that the solenoid is very long and is very tightly wound. By assuming it's very tightly wound, essentially for the sake of using Amperes Law, we're assuming that the current only has direction or components in the circumferential direction. So basically, this amounts to assuming current flows only in a circumferential direction. course, it's not only flowing in a circumferential direction, it has to have a longitudinal component as well, otherwise the current would not be able to flow from down here up to here, okay? So typically people treat this as a bunch of ring currents or current carrying rings stacked together, or you can treat it as something that has a surface current flowing over it. So if you treat it as a surface current, then the surface current density will be of the form N times I, where N is the number of turns per unit length. Okay, so what direction is the magnetic field going to point in? Again, you can use the right-hand rule, or we could use apply another argument. What are the possibilities? Well, the possibilities are in the circumferential direction, radial direction, and the z direction. Well, again, Biot-Savart Law tells us that the magnetic field is perpendicular to the current, so therefore, we eliminate this possibility. Now, what about the radial component? Well, let's assume for the sake of argument that for this particular configuration, the magnetic field has a component pointing in the radial direction. If I reverse the direction of the current, and the magnetic field is going to point towards the solenoid, well, changing the direction of the current is the same thing as turning this solenoid upside down. The magnetic field cannot depend on the orientation. It's not going to change from pointing inwards to outwards just because I turn the solenoid upside down. So I exclude this possibility as well. And I'm left with the only possibility that the solenoid or the magnetic field, due to a current carrying solenoid, has a component in the z direction. So where do I take my loops? Well, let's look at the outside region first. And here, just use your imagination. We'll just assume that there are wires run over the surface. Okay? Let's take an Amperian loop outside. Just determine that the magnetic field only has components in the z direction. So therefore, I can eliminate those two possibilities. Those aren't going to contribute anything to my interval. Now I need to look at the left and the right-hand sides. I can take my loop, make my loop as big as I want. So let's suppose I make this loop close to the solenoid, but I take the other side way, way far away. Well, I know that the magnetic field has to decrease in magnitude as I get very far away from the solenoid, so therefore the contribution from this side is going to be 0. Well, I've got 4 sides to the loop. There's no current flowing through this loop, so therefore I conclude outside the magnetic field vanishes. Now let's look at inside. And I'll draw my Amperian loop such that part of it's inside the solenoid and part of it's outside. Well, we know that the magnetic field has no component in the radial direction, so the top and bottom parts of the path contribute nothing. We've just determined that the magnetic field outside vanishes, and I'm left with one component here. But this time there is current flowing through it, and if we treat this as a surface current, the left-hand side of Amperes Law will give me B times L, assuming that the length of this path is equal to L. And then over the right-hand side, I have mu naught times the total amount of current flowing through it. So that's the surface current density, and I times the length. Therefore, we determine that the magnetic field has value mu naught I, and it's pointing in the z direction. Now for the last example, I'm going to calculate the magnetic field due to a toroid. And you'll notice that in all these examples I've worked, I generally speaking like to have the current flowing in the z direction, whether it's a long straight wire or it's a current sheet. And for a solenoid, I like to have the z-axis lying along the axis of the solenoid. In this case, I'm taking the z-axis as the axis of symmetry. So it's just personal preference there, but in any case, let's assume that we have a toroid that has a bunch of wires wrapped around it, and we'll assume that those wires, again, are very tightly wound. What that amounts to is that we can assume that the current doesn't have a component, this time in the circumferential direction. So last time when we did a solenoid, we assumed that the wires were so tightly wrapped that there was no longitudinal component to the current. It was only flowing in the circumferential direction. So this time, we're assuming that the current is flowing around the outside of the torus, and basically, our current is equal to IS in the S direction plus IZ in the Z direction. And let me modify this expression here. Let's take this. As such. And I'm going to write this out in terms of its, in Cartesian unit vectors. And by the way, following Griffith's lead here, I do like how he determines the direction of the magnetic field. Basically, everybody does, when you figure the Amperian loops for their long straight wire or current sheet, everybody does it pretty much the same way. But I especially like how he lays this out, so that's why I'm going to handle determining the direction of the magnetic field using his methods. So we'll assume that we're evaluating the magnetic field at some point in the xz plane. So in other words, r is equal to x caret plus z caret. Now r prime, our source, is going to be written as s prime cosine phi prime plus s prime sine phi prime in the y direction plus z prime z. I'm going to calculate the curl of the current, or rather not the curl, but the cross product of the curl and the separation vector. In order to glean some information, maybe find something that cancels out. So we'll have x, y, and z. Determining the x component of this cross product first. And now the y component. And finally, the z component. Okay, now let me make sure I tabulated everything correctly. So this times this, minus this times this. For the y component, this times this, minus this times this, negative sign up front. Z component, this times this, minus this times this. Okay, so when you're doing the integral, you're essentially adding up every bit of contribution. for every phi prime over here, there's another phi prime minus phi prime on the opposite side. Well, every term in the x component has sine phi prime. Every term in the z component has sine phi prime. So basically what you're doing when you're adding up all these components, you're adding up the sine phi prime, but there's always going to be a minus sine phi prime, because when you take sine of negative, it just becomes minus sine of that angle. So all those terms are going to drop out, and you'll just be left with the f component, or excuse me, the y component. Generalizing that to any particular plane, we'll see that magnetic field has a component only in the phi direction. So therefore, your Amperian loop will be a circle, and you know that every point on that circle that is concentric with the z-axis, or coaxial, I should say, with the z-axis, and the magnetic field is going to be constant at every point about that circle. So therefore, we will have 2 pi s times the magnetic field is equal to the total amount of current that flows through that. Well, we've got current I flowing in the wire, right? But you're going to have N turns all the way around. So it's actually going to be mu naught I N, and therefore the magnetic field is equal to mu naught I N over 2 pi s in a circumferential direction. It's not uniform inside the torus, but it is going to always be pointing in a circumferential direction. And it does go as basically 1 over s. Now what about outside? Well, if I take my Amperian loop outside, let's say lying in the xy plane, what you'll see is you've got current flowing upwards, but then you've got an equal amount of current flowing downwards, so the magnetic field vanishes outside. And of course, if you take your Amperian loop inside of this donut, inside where it's not intersecting with any of the surfaces, there's no current flowing through there either. So magnetic field vanishes outside and has this nice simple form in the interior region. I have a set of simulations posted online. You can find links to that at the BocaPhysics.com website, and it's called Amperes Law Simulations. And I basically go through every example that I've worked through just now, with the exception of this